What if I told you that figuring out how strong the concrete in a skyscraper is actually a lot like baking a cake? Yeah, it sounds a little wild, I know. But today, we're going to break down this super powerful statistical tool called regression, and we're going to do it by thinking of it as just a simple recipe. So let's jump in and see how this all works. Seriously, think about it for a second. You've got your flour, your sugar, your eggs all lined up. You kind of know how that cake is going to turn out, don't you? A little more sugar might make it sweeter. Just the right amount of baking powder is going to make it fluffy. You're already making a prediction based entirely on the ingredients. And this is where the whole idea just clicks. See, on the left with the cake, our goal is to predict its fluffiness and taste based on those ingredients. And on the right, with concrete, the goal is exactly the same. We're just using different words. We want to predict its compressive strength, which is just a fancy way of saying how much of a beating it can take based on its ingredients: cement, water, sand, and gravel. At the end of the day, it's just inputs and what you hope to get out. Okay, so how do we take this cool, intuitive idea of a recipe and turn it into something an engineer can really use? Well, that's where we translate it into the language of math. And here it is. This is the magic formula, a regression model that's just the formal name for our mathematical recipe. All it does is create an equation that connects the thing you want to predict, we call that your target, with all the things you already know, which are your predictors, or, your ingredients. What's so great about this is how perfectly it maps everything out for us. That cake fluffiness we were talking about, that becomes the concrete's compressive strength. That's our target variable, our Y. And all those ingredients, the cement, the water, the sand, those are our predictor variables, the X's. We're really just swapping kitchen terms for engineering terms. It's that simple. Now, as you can imagine, not all recipes are created equal. On the left, you've got something called simple linear regression. And look, it tries to predict strength using just one ingredient, like cement. That's like trying to predict how a cake will taste knowing only how much flour is in it. It's just way too simple for the real world, right? And that's exactly why we use the model on the right, multiple linear regression. It looks at all the ingredients at the same time, which, as you'd guess, is how things actually work. And this is where it gets really cool. When you use these smarter models, they start to tell you secrets hidden in the data. For concrete, the model figures out really fast that the ratio of water to cement is one of the most critical factors of all. A lower water to cement ratio almost always means stronger concrete. The math literally finds the secret ingredient in the recipe. Okay, so this all sounds great in theory, but how do you actually build one of these prediction machines? Well, it's not some kind of dark art. It's a pretty clear step-by-step process. Let's walk through it. So, it all starts with step 1, collect data. You've got to gather up all your past recipes and the lab results that show how strong they actually were. Then, step 2, you choose your predictors, basically which ingredients you think are important. Step 3 is where the fun starts. You train the model. You feed all that data into some software, and it crunches the numbers to find that perfect mathematical recipe. Step 4, super important, you validate the model to make sure it's actually accurate. And then finally, step 5, you use it. You can plug in a brand new recipe and get a strength prediction without ever having to pour a single drop of concrete. Okay, but that leads to a really important question, right? A prediction is totally useless if you can't trust it. So how do we actually measure the quality of our mathematical recipe? How do we know if we've got a 5-star formula on our hands, or just a total dud? Well, one of the big ones is called R-squared. Just think of it like a grade for your model, from 0 to 1. An R-squared of 0.85, like you see here, is actually fantastic. What this is telling us is that our recipe explains about 85% of why the concrete strength changes from one mix to the next. The other 15%? That might be due to things we didn't measure, but hey, explaining 85% of anything is a really solid place to be. The other number you need to know is the root mean squared error, or just RMSE. In simple terms, this tells us, on average, how far off our predictions are. So an RMSE of 5 megapascals means that if our model spits out a prediction of 40 megapascals, the real-world strength is probably going to land somewhere between 35 and 45. And for an engineer, that's a pretty tight window. That's super useful. All right, so we've built this awesome prediction machine. It's accurate, it's validated, but so what? Why does any of this math matter when you're out there actually building a skyscraper? Well, the impact is, honestly, it's massive. First off, it saves a ton of time and money. I mean, think about it. You're not physically mixing and testing dozens of different batches anymore. You're doing it virtually. This also lets engineers optimize their recipes for the absolute lowest cost. It acts like an early warning system on site, and it can even help drive sustainability by designing mixes that use less cement and create less waste. It's a huge deal. Okay, so what we've been talking about, multiple linear regression, that's like the workhorse. It's a fantastic foundational tool, but it's really just scratching the surface of a whole fascinating world of predictive modeling. Once you get the basics, you start getting into even more powerful stuff, like polynomial regression. That's for when the relationship isn't just a simple straight line. Then you've got things like random forests, which are brilliant at finding really complex ways that ingredients interact with each other. And then there's the big one, artificial neural networks, which can find incredibly subtle patterns, but you need a ton of data for those. The toolbox just gets deeper and deeper. So at the end of the day, this quote really nails it. A regression model is nothing more than a data-driven mathematical recipe book. It just takes all the guesswork out of the process and replaces it with a reliable formula that's built on cold, hard evidence from the past. And the really cool thing is, this whole way of thinking, this recipe idea, it doesn't just work for concrete. You can use it pretty much anywhere you've got data and a question you want answered. And that kind of leaves us with one last, really fascinating question. If we can write a mathematical recipe for concrete, what other parts of our world are just waiting for the right recipe to be discovered?